Okay, so now we're experts at creating simple linear regression models for variables that we know are correlated. And that's great, but beyond the correlation, which just has to do with the relationship between the variables, we have no way of evaluating how well our model actually predicts. So we're going to see a series of metrics that we can use to both determine if we are willing to use a model and to compare between models to see which one is better. And the first of these metrics is R squared. Now, R squared, or the coefficient of determination, measures how much better the regression model is at estimating Y values than our previous best estimate, which was the mean. And this is also known as the goodness of fit indicator, as it lets you know how well your line fits the sample data or how close it is to its points along the scatter plot. So naturally, the higher the R squared value is, and this can be anywhere between 0 and 1, then the more confident that you can be in the accuracy of your predictions. So if we look at our previous examples and their correlation coefficients, we can put a line through them and get their R squared values, which you can calculate by just squaring the correlation. So what do these mean? Well, a lot of the time you'll see them expressed this way. Digital ad spend explains 73% of the variation in site traffic. That's what the R squared value tells us. So it can be used to predict it. In this case, digital ad spend only explains 25% of the variation in offline ad spend. So it likely won't predict it very well, at least not much better than the mean. And here, digital ad spend doesn't explain any of the variation in site load time and shouldn't be used to predict it. And as you can see from this line here, this is no better than the mean, which is precisely a horizontal line. So that's why I like to think of the R squared value as how much better the model is at predicting than the mean. And let me illustrate that further. Aside from being the square of the correlation, R squared can be calculated by using this formula, which is 1 minus the sum of squared error, which if you recall is the distance between the values and the regression line, divided by the sum of squared total, which is the distance between the values and the mean line. So this right here is the variation of Y around its mean, which is what the normal variation is for a variable. But this is the variation of Y not explained by X. So if you compare both graphics, you can see that the regression line eliminates a lot of the variation and leaves much smaller distances or errors. So as this decreases relative to the regular measure, as the variation of Y not explained by X gets smaller, then the value of R squared increases. And you can see it in the formula. If the sum of squared error, which is the numerator, is small compared to the sum of squared total, which is the denominator, well then the fraction will be small, so you will subtract a small number from 1, leading to a large R squared value. But if they are almost the same size, and X doesn't really explain any of the variation in Y, well then the fraction will be very close to 1, and you will have a small R squared value. And that is why R squared ultimately measures how much better the regression model is at estimating expected values than the mean. So now let's go over to Excel and calculate this R squared value for one of our regression models. So here in Excel, I'm going to jump to the link on R squared. And I'm going to stick with our old model for these examples where we're predicting employability after scores using employability before. That way you can continue to use this model that predicts the improvement, which is much more helpful, in the assignments for this section. So we have the correlation, we have our regression model, we can make predictions. Time to start evaluating how well this model predicts, starting with the R squared value. Now, there are many ways you can calculate this, the first of which is just grabbing the correlation coefficient, which is R, and then just squaring it. So we get a value of 0.9003, which is a very good r squared value. We can also use the r squared function, grab the known y's, the known x's, and we get the same value. We can also do it in our scatter plot here the same way we added the equation. If I go to format the trend line, and I scroll down, you'll see that you can display the r squared value on the chart. In this case, again, we get 0.9003, so same exact thing. But what I also want to do is calculate the sum of squared error and the sum of squared total and calculate r squared that way, just because these are going to come in handy as we calculate more model evaluation metrics. So the sum of squared error is the sum of the square distances between the points, which are the employability after values, and the line. So to calculate it in a single formula, we can actually use a function called sum squares, which is this one right here. And then all we need to do is provide the differences, which is going to be these y values here, minus our y hat values. Now we don't have those anywhere, but what we can use is use the forecast function to calculate them. So the x is going to be our known x's. We're going to predict all of these. Our known y's are these. Our known x's are again these. So we're going to return the prediction for all of these and then compare it to the actual value. Then square them, then return the sum. So we get a sum of squared error of 81,000. Now let's get the sum of squared total. So again, sum of the squares, but in this case it's the difference between the values and the mean. So it's just the average of all of these values. And we get 822,000, which is much larger than our sum of squared error. So this is our total variation of y, and this is the variation of this y that isn't explained by this line, which isn't a lot. So if we grab 1 minus this division, then we get the same exact r squared value, which tells us that this model is 90% better at predicting the employability after scores by using the employability before scores than if we just grab the mean of employability after. In fact, let me calculate that. So if we were to just use this, then we'd predict 289. We could also grab a confidence interval and maybe grab a wider range. But if we use this, let's say for scores of 120, then our prediction is much lower and much better than this average, and the same applies, for example, for employability before values of 400, for example. Now we're predicting 454, which makes a lot of sense, instead of just the average, which is 289. Which again shows not just the power of regression, but how we can use these evaluation metrics to get an idea of how effective or accurate this model is. Alright, time to talk about one of the crazier words in all of statistics, homoscedasticity. Now, for all of its letters, homoscedasticity simply means that the scatter of the data points is the same along the entire regression line, which is necessary in order for the model to generalize well and make accurate predictions across the full range of x values. So for simple linear regression, this is easy enough to visualize from the scatter plot. If we look at the regression model for this data here, well then you can tell that the scatter is consistent over the entire x range. But if we look at this one, then you can see this sort of cone shape where the scatter spreads out as x increases. And another way to look at this is by using the residual plots, which are a special type of scatter plot used in regression analysis that uses the residuals or errors in the y-axis instead of the dependent variable. So in the first one, which is homoscedastic, then you can see that the residuals have consistent variance. In fact, the residuals actually follow a normal distribution along the line with a mean of 0 and a standard deviation equal to the standard error of the regression, which is why we can create those confidence intervals around our estimates like I mentioned in the previous lecture. But if a dataset shows heteroscedasticity, then that no longer applies, which is why it's so important to check this. So I'm going to jump over to Excel so we can do a quick visual check on the homoscedasticity of our regular scatter plot, but we will see examples of residual plots pretty soon. So let's just take a quick look here. I'm going to go to the homoscedasticity link. And let's focus on our scatter plot here. We have our data points, we have our regression line, and it does look like the scatter along the line is pretty consistent. So I think that we're good to go here, and this shows that the data is homoscedastic. All right, time to talk about an old friend of ours, the standard error. In regression, the standard error is the average distance between the line and the data points. In other words, and this will sound like a familiar definition for the standard error, it is the standard deviation of the sample values around the regression line. Isn't that awesome? And the best part is that it's a good intuitive measure of how well your model predicts, or rather how much its prediction is off by on average. Now, the formula is really intuitive as well. The standard error, which is the capital S here, it's just the square root of the mean square error, making it just the mean error, basically. And to calculate the mean square error, we just take the sum of the squared error, which we know how to calculate now, and divide it by the degrees of freedom, which is just the sample size, minus the number of independent variables, or x's, minus 1. Or you can use the stakes, S-T-E-Y-X function, which we saw earlier and is clearly much easier. But that's it. So let's try calculating this in Excel. I'm going to go to the link on standard error. And I'm going to start by calculating it long form. So I am going to calculate the mean square error and then get the square root. So to do that, we just grab the sum of square error and divide by the sample size, which I don't think I have anywhere. So let's count these values. I can use either one. Minus the number of independent variables. In this case, I only have 1, which I'm using to predict the y. So 1 minus another 1. Close that. We get a mean squared error of 881, which makes the standard error the square root of that. So that's the standard error. Again, we can also calculate by using this function here, in which we just provide the known y's, the known x's, and we get the same exact result. But what does this tell us? Well, we know that the predictions from our model are off by 29.68 on average, which isn't too bad and it is helpful, but it's actually more helpful than you'd think. If we go by the empirical rule, which applies here as well, then we can expect 78% of the students with employability scores before the program of 250 to get employability scores after the program between around 270 and 330. So if you remember from the empirical rule, 68% of the values live within one standard deviation of the mean. So all I need to do is subtract one standard error, add one standard error, and that gives us a 68% confidence interval for this prediction. And if we continue to use the empirical rule, we know that 95% of them will get scores between 240, so this minus this times 2, and 360. And if that isn't the perfect culmination of everything we've learned, then I don't know what is. So that's the standard error for you. All right, time to revisit a familiar topic, the hypothesis test. Regressions actually include an implied hypothesis test in which the null hypothesis states that no relationship exists between the dependent and independent variables. So, in other words, you are trying to find significant evidence to prove that your regression model isn't useless, that a relationship does exist. And in order to trust the results of the test, you actually need to check that your data is homoscedastic, which is another part of the reason why we discussed that topic in the previous lecture. But other than that, these steps for the test are exactly the same. We already mentioned the null hypothesis, which is that no relationship exists between the variables. So the alternative is that a relationship does exist. Now, next, as always, we need to set a significance level, which, if you recall, is the accepted probability of committing a type 1 error, which in this case is thinking that the model isn't useless when it actually is. So now all we need to do is figure out how to calculate the test statistic and its p-value to be able to draw one of these conclusions, to either reject the null hypothesis, which would make us confident that the model isn't useless, or to fail to reject it, meaning that it most likely is. So let's start with the test statistic. Now, the test statistic here isn't a t-score or a z-score, but an f-score for your sample in the regression model. And it's essentially the same thing. It's the standard deviations between your model and the hypothesized useless model, but for an F distribution, which we don't really need to go into detail about. What you do need to know, though, is that to calculate the F-score, you divide the mean square regression, which is the variability explained by the model, by the mean squared error, which is the variability not explained by the model. So another way to think of this is as the ratio of variability that your model explains versus the variability that it doesn't explain. So if that ratio is high and it explains a lot more than it doesn't, well then the F-score will be high and we'll get a very small p-value. Now, we already know how to calculate the mean squared error. We did that in the standard error lecture, which means that we just need to see how to calculate the mean squared regression. And all we need to do here is grab the sum of squared total and subtract the sum of squared error. And this entire numerator, this subtraction, is known as the sum of squared regression, which you can think of as the distance between the mean and the regression line. So all we need to do is grab that and divide by q, which is just the number of independent variables. So that's how to get the test statistic. Time to calculate its p-value. Now, in regression, the p-value is the probability that your model is useless. In other words, the likelihood that you got a relationship this strong when no relationship actually exists. So the lower the p-value, the stronger the evidence that a relationship does exist. And the good news is that we pretty much know how to calculate this already. In the past, we've used t.dist or norm.s.dist. Here we're going to use f.dist.rt every single time. We're going to plug in our test statistic, plug in the number of independent variables, then plug in the degrees of freedom, and we get our p-value. And as always, this is going to prompt the important reminder to set the significance level before calculating the p-value. That way you're not manipulating the tests of the result and getting the conclusion that you were looking for. So that was a lot, but let's walk through these steps in Excel so we can solidify everything. So here in Excel, we're going to go to the hypothesis test link under regression analysis. And we want to know if we can be at least 95% sure that this relationship between these two variables that we built our regression model on isn't just down to random chance. So with this 95% confidence level, we'd be setting an alpha or significance level of 0.05, which is 1 minus 95%, which means that now we need to calculate the test statistic, which is the mean squared regression. So let's start there. That's going to be the sum of squared total, which we already have. Let me open parentheses first. Sum of squared total minus sum of squared error divided by the number of independent variables. In this case, it's only one. And for the test statistic, we can divide the mean square regression by the mean square error, which is right here. Right off the bat, you can tell that the variability explained by our model is much higher than the variability that isn't explained, so we're going to get a very large test statistic. We get 840, which is insane if you think about it. This is 840 standard deviations away from the mean. We've never seen anything like this. So for the p-value, we're going to use f.dist.rt. The x is going to be our test statistic. Degrees of freedom 1 is the number of independent variables. Again, that's 1. And the degrees of freedom is our sample size, which I should have calculated somewhere, but let's just grab it here. So sample size minus number of independent variables, which is 1, minus another 1. And we get a p-value of essentially 0. So what does that tell us? Well, since p is less than alpha, then we reject the null hypothesis that our model is useless, which, as far as we know, confirms that a relationship does exist and this regression model is useful to us, so we should use it for our predictions. Alright, time for an assignment on model evaluation. Nick is back and he can't believe that we're able to predict employability improvements based on undergrad grades, so he wants to make sure that we can trust this model. Can we check with a 95% confidence? Well, we sure can. So key objectives: to calculate the R-squared value, to calculate the standard error, to confirm the homoscedasticity, to run a hypothesis test, and to draw a conclusion on the accuracy of the regression model's predictions. So let's go do that. Alright, time to wrap up the course by talking about multiple linear regression. Now, I'm keeping this as a pro tip since regression is a highly complex and nuanced topic that could warrant its own course. In fact, we have a complete conceptual regression course at Maven as part of our machine learning foundations path. So I'm just going to introduce the topic here and show you how you can build these types of models in Excel. Now, multiple linear regression is used for predicting a single dependent variable based on multiple independent variables. So in other words, it's the same linear regression model, but with additional x variables. Literally. This is the simple linear regression model that we saw before, and this is the multiple linear regression model. So instead of just one x, we have a whole set of independent variables and their associated coefficients that we can use to predict the dependent y variable, which is still just 1. And to visualize how multiple linear regression works with just 2 independent variables, imagine fitting a plane instead of a line through a 3D scatter plot like this one. You can see that we have the 2 independent x variables at the bottom, and then the plane that passes through the points to try to predict the dependent y variable. So a scatter plot, very easy to read. This, maybe not crazy, but still a lot more difficult. Now imagine even more independent variables. Impossible, right? We can't even fathom how you'd start to look at this in 4D or 5D or anything more than that. And the truth is that multiple linear regression can scale well beyond 2 variables, so the visual analysis will no longer be feasible. So we have to rely on being able to read the model evaluation metrics to determine if the model is any good or not. That's why it's so important to understand them all. And the multiple linear regression model actually has 2 additional metrics to evaluate. The adjusted R-squared, which penalizes the regular R-squared value based on the number of independent variables used in the model. Curiously enough, if you just throw an infinite number of variables at a regression model, then you're bound to get a high R-squared value, So the adjusted R-squared makes you take a step back and really think about which variables are worth including. Because more often than not, the simpler model is the better model. Which brings us nicely to the next metrics, which are the coefficient p-values. And what these do is show the probability that each independent variable is meaningless in the context of the regression. So the lower the p-value, the more that you can trust that coefficient or that independent variable. So let's take a look at these with an example from our project. Let's say that we wanted to predict the employability after based on the undergrad grade and the employability before, which are the two things we have on a student as they apply to our program. Well, we can plug the data from our sample into Excel's regression tool, and we would get an output like this one, which we now know all about. So this is the model itself. If we wanted to predict the employability after, we can take the undergrad grade, multiply it by about 3.65, then add the employability score before multiplied by 0.99, and then subtract 222. That's our prediction. But to check if that model is any good to use, then we have metrics like these, which is the goodness of fit, or R-squared. In this case, 98.5, which is massive. It means that the model explains almost all of the variation in the employability after scores. And you can see that the adjusted R-squared is very similar, since we only have one extra independent variable. We also have the standard error. So on average, our model mispredicts by 11.33, which is nothing really. If we think about the magnitude of our employability scores, which range from 0 to 500. We have the F significance as well, or the p-value for the entire model. And this right here is, in scientific notation, it means 1.72 times 10 to the negative 85. So imagine right around 85 zeros before the decimal number here. So even if we had an alpha of 0.000001, which we would have to set before running all this, we'd still reject the null hypothesis and confirm that this model isn't useless. And then we have the p-values for each coefficient, which in this case are pretty much 0 as well. So what does this all tell us? Well, that this is a really good model that we can use to predict the employability scores for these students in our next class and determine who we accept into our program. All, of course, to maximize the placement rates once they graduated, since we notice that the higher they are, the more likely they are to get placed, at least quickly. So that's it for multiple linear regression. Let me quickly do this same example in Excel just so you see how exactly to execute it, and then we can call it a day. So I'm going to go to the final link in our Excel statistics workbook on multiple linear regression. We have the undergrad grade, the employability before, and let's see if we can use them to predict the employability after. So again, data analysis. Let's select regression here. Okay. We do have a nice blank slate this time around, so the input range is going to be the employability after. For Y, that's what we're trying to predict. The X range are going to be our independent variables, and you have to make sure to have them side by side as I do here, because we're going to select them in a single swoop. So undergrad grade, employability before, select them both. We are including the labels in the selection. Let's add the residual plots, and let's have the output range be right here. Let's press OK. And we get this message. I don't think I'm going to overwrite anything here. Yes, it will, but it doesn't matter. Let me just expand these columns. And we get the same model and these same metrics that we've already evaluated. We can take a look at the residual plots as well. Uniform and around 0. Uniform and around 0. So we're all set there. Now let's see if we can predict some of these. So I'm just going to rewrite what I had a few seconds ago. So undergrad, grade. I'm just going to do before. And we want to predict after. Let's make this nice and bold. So if a student, let's say, has an undergrad grade of 70 and an employability before of 285, what can we expect his employability after to be? Well, we have the intercept plus, so that's our beta 0, plus beta 1 times x1 plus beta 2 times x2. Press enter and we get a predicted score of 315. And that is multiple linear regression in a nutshell for you. Alright, so I have to admit I have been misleading you guys a bit in making you think that you need to do all of these calculations yourself in order to build a regression model in Excel. The truth is there's a native tool that Excel has specifically for that purpose. But the reason that I wanted to walk through this step by step is so that you would understand exactly what each component means and its relationship to how these two variables, the dependent and independent variables, interact with each other. So that way we can interpret these results accurately and intuitively. So let me show you how to do this the traditional Excel way with the analysis toolpack. And that is going through data and to the data analysis toolpack option here. You might not have this here yourself. If you don't, you can go to File, Options. Here in the options, you can go to the add-ins. You'll see that I have the analysis toolpack here. You can go down here to Manage Add-ins, go, select the analysis toolpack, press OK, and you should have it pop up here. So again, data analysis toolpack. We're going to get this window here. There's a whole bunch of things that we can do. We're interested in the regression option here. Let's press OK. And you'll see that I had already done this, but I'm going to start again from scratch. So we're going to start by inputting the Y range. This is our dependent variable. In this case, again, the employability after. And you can select that with the column header, because we can then select this labels option that lets Excel know that the first row is for the name of the variable. The X range is already selected, but let me do it myself as well. So again, let's select this labels option. I'm going to enable this option to add the residual plots, and that way we can test the homoscedasticity. And I'm going to select the output range. I think by default it's going to be in a new workbook. I'm just going to have it display right here so that we can compare these metrics to the results of our regression model here. So let me just select this cell here. Press OK. You'll see that it calculates everything in seconds. You don't need a single Excel formula. Let me show you all this stuff. And hopefully by looking at this, you'll understand why I dove into each of these specifically in separate lectures versus just starting with this gigantic pool of numbers. But now we actually do know what we're looking for and what everything means. So let's start in the top. This multiple R here is actually just the correlation, and I can show you that we get the same exact number. We have the R squared, which is right here. The adjusted R squared I'm going to talk about when we dig into multiple linear regression. It's not really relevant right now. We have the standard error, and then check it out. We have all of the sum square metrics. So this is the sum square regression, which is this right here. You'll notice it's the same as the mean square regression since we're dividing by one independent variable. We have our F statistic, which is this one right here. And the F significance is another name for the p-value in the context of the hypothesis for a regression. We also have the mean square residual or the mean square error, which is this right here, 881. We have the sum of square error, which is this right here. And we have the sum of square total, which is this right here. So we have all of these same model evaluation metrics at a single glance here, but now we know exactly what each of these means. The only remaining part is the actual coefficients here, which is the model itself. So we have the y-intercept, which is 41.63. We knew that. And we have the coefficient for the employability before, which is our only independent variable here. So that's going to be this slope here of 1.03. I'm not going to dive into the rest of these yet, but since I did select the residual plot option, it's going to plot all of these residuals here and give me this residual plot, which is like we saw in the past. And if we analyze it quickly, we can see that they are centered around 0 and they are scattered pretty evenly. We're not seeing a cone shape that could concern us or indicate that there's some sort of heteroscedasticity here. So that's the analysis toolpack option for you guys. We're going to continue to see this as we dive into multiple linear regression. It ultimately leads to the same exact thing, just with fewer clicks. So feel free to use this option going forward. I'm just happy that now you know how you can read this and determine if your model is any good or not, and if you can use these coefficients to start making some predictions.